Hello there, grade 10. We meet again. I am G10 and we're here again to learn something new about mathematics. I'll be your guide as you go through this e-module. Just like last time, you can see at the right side the tabs where you can choose your preferred topic, but I suggest that you go through all of the lessons, to maximize your learnings. The tab consists of discussion, examples, and worksheets where you can practice your new acquired knowledge. Let's start. What is a polynomial function? A polynomial function is a function of the form where a sub n is not equal to 0. A sub n times x raised to n is the leading term. A sub n is the leading coefficient. A sub 0 is the constant term. A sub 0, a sub 1 up to a sub n is the coefficients, and must be real numbers. And n is a positive integer. Other than p of x. A polynomial function may also be denoted by f of x. Sometimes, a polynomial function is represented by a set p of ordered pairs x, y. Polynomials may also be written in factored form and as a product of irreducible factors, that is, a factor that can no longer be factored using coefficients that are real numbers. Study the given examples below. The terms of a polynomial may be written in any order. However, if they are written in decreasing powers of x, we say the polynomial function is in standard form. Examples: f of x equals 3 minus 11x plus 2x squared. To make it in standard form, just write the terms in decreasing power of x, that will be f of x equals 5x squared minus 11x plus 3. By looking at the standard form of the polynomial function, the leading term is 5x squared. The degree is 2. The leading coefficient is the coefficient of the leading term, which is 5. The constant term is the term with no variable, that is 3. Next example. F of x equals 2x cubed over 3 plus 5 thirds plus 15x. Arrange the terms in decreasing power of x. We have f of x equals 2x cubed over 3 plus 15x plus 5 thirds. By looking at the standard form of the polynomial function, the leading term is 2x cubed over 3. The degree is 3. The leading coefficient is 2 thirds. The constant term is 5 thirds. Next, p of x equals x times the quantity of x squared minus 5. To get the standard form of the polynomial function, just multiply the monomial x to the binomial x squared minus 5. The answer is p of x equals x raised to 4 minus 5x. The leading term is x raised to 4. The degree is 4. The leading coefficient is 1. The constant term is 0. Next we have p of x equals negative x times the quantity of x plus 3 times the quantity of x minus 3. Simplify the given polynomial function. P of x equals negative x cubed plus 9. The leading term is negative x cubed. The degree is 3. The leading coefficient is negative 1. The constant term is 9. For the last example we have p of x equals the quantity of x plus 4 times the quantity of x plus 1 times the squared of quantity of x minus 1. In standard form, that is, p of x equals x raised to 4 plus 3x cubed minus 5x squared minus 3x plus 4. The leading term is x raised to 4. The degree is 4. The leading coefficient is 1. The constant term is 4. There are two important features of the graphs of polynomial functions. The first feature is that the graph of a polynomial function is continuous. Essentially, this means that the graph of a polynomial function has no breaks, holes, or gaps. It can be drawn without lifting your pen from the rectangular coordinate system. The second feature is that the graph of a polynomial function has only smooth and rounded turns. A polynomial function cannot have a sharp turn or corner. There are many other things to consider when we draw the graph of a polynomial function. The first one is using the intercepts and the rational root theorem. The intercepts are the points at which the line or graph touches or intersects the axis. The rational root theorem states that if p divided by q, in lowest terms, is a rational root of the equation, then p is a factor of the constant term a sub 0 and q is a factor of the leading coefficient a sub n. The x-intercept. The x-intercept of the graph is the value of x when y equals 0, thus, the point where the graph intersects or crosses the x-axis. The y-intercept. The y-intercept of a polynomial function is the value of y when x equals 0, thus, the point where the graph intersects or crosses the y-axis on the coordinate plane. The y-intercept is always the constant term of a polynomial function when it is in standard form. If there is no constant term in a given polynomial function, then the y-intercept is 0. Example 1. Find the intercepts of p of x equals x cubed minus 4x squared plus x plus 6. Solution. To find the x-intercepts, set y equals 0. Remember that p of x equals y. Factor the polynomial completely using the rational root theorem. We get the factored form of the polynomial function as the quantity of x plus 1 times the quantity of x minus 2 times the quantity of x minus 3. Apply zero product property, that is, equating each factor to 0 to determine the value of x. Then we have x equals -1, x equals 2, and x equals 3. Therefore, the x-intercepts are -1, 2, and 3. This means the graph will pass through -1, 0, 2, 0, and 3, 0. To find the y-intercept, set x equals 0. This is simpler than finding the x-intercept. Notice that when you set x equals 0, and the given polynomial is in standard form, the y-intercept is the constant term 6. Therefore, the y-intercept is 6. This means the graph will also pass through 0, 6. Let us graph the polynomial function p of x equals x cubed minus 4x squared plus x plus 6 to prove the concept. Given p of x equals x cubed minus 4x squared plus x plus 6. Y-intercept is 6. X-intercepts are -1, 2, and 3. This is now the sketch of the graph of the given polynomial function using the intercepts. Example 2. Find the intercepts of the polynomial function. F of x equals x times the quantity of x plus 6 times the quantity of x plus 1 times the quantity of x minus 1. Solution. To find the x-intercepts, set y equals 0. Remember that f of x equals y. The given polynomial is already in factored form, so, apply zero product property or equate each factor to 0 to determine x. We have x equals 0. X plus 6 equals 0. Then x equals -6. X plus 1 equals 0. Then x equals -1. And x minus 1 equals 0. Then x equals 1. Therefore, the x-intercepts are -6, -1, 0, and 1. This means the graph will pass through -6, 0, -1, 0, 0, 0, and 1, 0. To find the y-intercept, set x to 0. Remember that any number multiplied by 0 is 0. Therefore, the y-intercept is 0. This means the graph will also pass through 0, 0. Let us graph the polynomial function. Given f of x equals x times the quantity of x plus 6 times the quantity of x plus 1 times the quantity of x minus 1. Y-intercept is 0. X-intercepts are -6, -1, 0, and 1. This will be the sketch of the graph of the given polynomial function. Click the SAQ button at the right for self-assessment questions. Other things to consider when we draw the graph of a polynomial function are the end behavior of the graph and the leading coefficient test. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. The leading coefficient is significant compared to the other coefficients in the function for the very large or very small numbers. So, the sign of the leading coefficient is sufficient to predict the end behavior of the function. This is known as the leading coefficient test. Look at the illustrations below. On the first figure, if the degree of the polynomial function is even, example 2, 4, 6, and the leading coefficient is positive, the end behavior of the graph rises to the left and rises to the right. On the second figure, if the degree of the polynomial function is even, example 2, 4, 6, and the leading coefficient is negative, the end behavior of the graph falls to the left and falls to the right. On the next figure, if the degree of the polynomial function is odd, example 3, 5, 7, and the leading coefficient is positive, the end behavior of the graph falls to the left and rises to the right. On the last figure, if the degree of the polynomial function is odd, example 3, 5, 7, and the leading coefficient is negative, the end behavior of the graph rises to the left and falls to the right. Example 1. Find the end behavior of the function x raised to 4 minus 4x cubed plus 3x plus 25. Identify the degree and the leading coefficient. Make sure that the function is already written in standard form. As you can see, the degree is 4. Width is even. The leading coefficient is 1, which is positive. Therefore the end behavior of the graph rises to the left and rises to the right, or opens upward. This is the sketch of the graph of the function. Example 2. Sketch the graph of f of x equals -2 times the squared of the quantity of x plus 3 times the quantity of x minus 5. Write the function in standard form. Just multiply all the factors of the function. The answer would be f of x equals -2x cubed minus 2x squared plus 42x plus 90. Identify the degree and the leading coefficient. As you can see, the degree is 3. Width is odd. The leading coefficient is -2, which is negative. Therefore the end behavior of the graph rises to the left and falls to the right. This is the sketch of the graph of the function. Click the SAQ button at the right for self-assessment questions. Another things to consider when we draw the graph of a polynomial function are the multiplicity of roots. The multiplicity of each zero or roots is the number of times that its corresponding factor appears. In other words, the multiplicities are the powers. The point of multiplicities with respect to graphing is that any factors that occur an even number of times are squares, so they don't change sign. Squares are always positive. This means that the x-intercept corresponding to an even multiplicity 0 can't cross the x-axis, because the 0 or roots can't cause the graph to change sign from positive, above the x-axis, to negative, below the x-axis, or vice versa. Look at the illustrations below. All four graphs have the same zeros. At x equals -6. And at x equals 7. But the multiplicity of the 0 determines whether the graph crosses the x-axis at that 0. Or if it instead turns back the way it came. For the first figure the roots -6 and 7 appears only once, so it crosses the x-axis. For the second figure notice that the roots or zeros of 7 occurs twice. Multiplicity 2, that is why it cannot cross the x-axis. For the third figure the roots or zeros of -6 occurs twice. Multiplicity 2, that is why it cannot cross the x-axis. For the last figure -6 and 7 has even multiplicity, which is 2. That is why the graph turns back and cannot cross the x-axis. Remember that if R is a zero of odd multiplicity, the graph of p of x crosses the x-axis at R. If R is a zero of even multiplicity, the graph of p of x is tangent to the x-axis at R. Click the SAQ button at the right for self-assessment questions. Another things to consider when we draw the graph of a polynomial function is the number of turning points. The graph of a polynomial function may have a turning point where the graph changes from increasing to decreasing, or decreasing to increasing. Look at the illustration at the right. That is the graph of the polynomial function. F of x equals x raised to 4 minus x cubed minus 4x squared plus 4x. The function is a fourth-degree polynomial function and has 3 turning points. Remember, the graph of a polynomial function of degree n has at most n-1 turning points. If the degree of the polynomial is 7, then it has at most 6 turning points. If the degree is 9, then it has at most 8 turning points. If the degree is 10, then it has at most 9 turning points. And so on. Keep in mind also that a polynomial graph can have fewer than n-1 turning points. But it will never exceed n-1 turning points. Example: if the degree is 5, the possible number of turning points is at most 4. It can be 4, 3, 2, 1. But will never be 5 and above number of turning points. Click the SAQ button at the right for self-assessment questions. In graphing polynomial function, you have to consider also the intervals and the table of signs. We can find the signs of the values of the polynomial functions in each interval. The signs of the values will tell us whether the graph within the interval is above or below the x-axis. Example: sketch the graph of the polynomial function p of x equals the quantity of x plus 4 times the quantity of x plus 2 times the quantity of x minus 1 times the quantity of x minus 3. Solution: the roots are x equals -4, -2, 1, and 3. These are the only values of x where the graph will cross the x-axis. These roots partition the number line into intervals. Test values are then chosen from within each interval. The first interval is -4 to -infinity. The second interval is between -2 to -4. The third interval is between 1 to -2. The next interval is between 1 to 3. And last interval is 3 to +infinity. Given the polynomial function p of x equals the quantity of x plus 4 times the quantity of x plus 2 times the quantity of x minus 1 times the quantity of x minus 3. The partitions or intervals will be -4 to -infinity, between -2 to -4, between 1 to -2, between 1 to 3, and 3 to +infinity. For the test value, think of a number that is within the given interval. For the first interval -4 to -infinity we will use -5. For the second interval between -4 to -2 is -3. For the third interval we have 0. Between 1 and 3 use 2. For the last interval 3 to +infinity use 4. To determine the signs for each partition and its position relative to the x-axis, use the test values. Just replace the variable x with the given test value in the polynomial function. For the first interval x equals -5. Substitute the value of x to the polynomial function. P of x equals the quantity of x plus 4 times the quantity of x plus 2 times the quantity of x minus 1 times the quantity of x minus 3. Solve and simplify. -5 plus 4 is -1. -5 plus 2 is -3. -5 minus 1 is -6. And -5 minus 3 is -8. Then p of -5 equals 144. Or used only the sign of each factor. Negative times negative times negatives times negative is positive. The sign is positive, which means part of the graph is above the x-axis. For x equals -3 use the same process. P of -3 equals -24. The sign is negative, which means part of the graph is below the x-axis. For the test value of the third interval, x equals 0. P of 0 equals 24. The sign is positive, which means part of the graph is above the x-axis. For the test value of the next interval, x equals 2. P of 2 equals -24. The sign is negative, which means part of the graph is below the x-axis. For the last interval we have x equals 4. Therefore, P of 4 equals 144. The sign is positive, which means part of the graph is above the x-axis. We can now sketch the graph of the polynomial function. For the first interval, -4 to -infinity. The location of the graph is above the x-axis. For the second interval, between -2 to -4. The location of the graph is below the x-axis. For the third interval, between 1 to -2. The location of the graph is above the x-axis. For the interval between 1 to 3. The location of the graph is below the x-axis. And for the last interval, 3 to +infinity. The location of the graph is above the x-axis. Plotting this on a Cartesian plane, the graph of the polynomial function is where the x-intercepts are -4, -2, 1, and 3. Y-intercept equals 24. The end behavior is rising to the left, rising to the right. The multiplicity of roots are, since the roots only occur once, all four will cross the x-axis. The number of turning points is 3. The intervals and the position of the graph relative to the x-axis. Click the SAQ button at the right for self-assessment questions.